Thank you very much. As somebody who grew up in the Midwest and now lives in New York, it's really nice to be back in the Midwest. But as somebody who grew up in Lincoln, Nebraska, it pains me to say that I do like being in Columbia and the University of Missouri does have a free campus, but none of my friends have said that. So my name is Graeme. I'm with the University of Illinois Chicago, where we manage the Department of Energy's Onsite Energy Technical Assistance Partnership for EPA's Region 5 and 7, or that's another way of saying this, the broad Midwest. So I'll be talking today about the Onsite Energy Technical Assistance Partnership Program, who we are, what we do, and then really going through a number of case studies for successful installations of on-site energy at industrial facilities. So the primary purpose of our program is to work with industrial facilities to identify on-site energy opportunities to help save money, boost resiliency, all these good things. We also work with a number of other energy users that I'll go into as well. So some background. So the Onsite Energy Program, the Onsite Energy Technical Assistance Partnership, or TAP for short, has its roots going back to 2004. We used to just be focused on a technology called combined heat and power, and now we are focused on all of the technologies you see on the screen. The big reason the Department of Energy has created this program and inspired this program today is that on-site energy provides a number of benefits for sites, for businesses in the United States. The number one that we promote, and the reason that businesses are installing this equipment, is the first bullet you see and the top of the circle, cost savings. A lot of businesses we work with, a lot of our institutions we work with might have other goals, resiliency, sustainability. But at the end of the day, it's always cost savings that drives projects and helps projects pencil out. So the Department of Energy thinks that on-site energy is important for promoting cost savings. We're making our manufacturing and industrial sector more competitive. Related to this is resiliency, reliability, and resiliency. We want these businesses to be able to survive if the grid goes down. We want them to have cheaper energy prices, more resilient energy, especially in times where we see low growth in MISO and the PJM region, to have that resiliency in case of, God forbid, a blackout during peak summer outages. Sustainability and energy independence are also key reasons that we see businesses promoting and going on-site energy, and the Department of Energy supporting it. There's also great support, community engagement, and innovation. So what is the TAP program and who we are? Well, we're a network of centers throughout the country, universities or nonprofits. We have three overlying missions, three key missions. The bread and butter of what we do is provide technical assistance. And so that's working with end users, that's working with businesses to help analyze their energy profiles to determine is on-site energy going to be a good solution for their facility. And if so, what technologies are we talking about? Now we work hand in hand with the folks in the physical plant, in the facilities, to understand how they're using energy, not just electricity, but thermal energy, electricity, what their chilled water profile, which is steam and hot water profile, what technologies would they like us to look at, and what technologies do they not want us to look at because of some bad experience in the past. So that's the bread and butter. We provide these detailed reports for sites to help them make decisions, educated decisions on if they should proceed with on-site energy or not. One of the other key aspects that we do is work with end users to educate about the various different types of on-site energy. I keep saying on-site energy is very broad term. It not only comprises what everybody can understand, solar PV is really easy to understand, it's on-site energy solution, and so is wind. But also it does heat pumps, thermal storage, like thermal hot water storage, or thermal hot brick storage, electric storage, like batteries. Combined heat and power is sort of the core of what we do, so natural gas fired combined heat and power. And a number of other technologies that are emerging on the market today. And then key to our goal as a TAP is we educate stakeholders on on-site energy opportunities and barriers within their region. So currently we're working with the Illinois, the ICC Commerce Commission, the Illinois Commerce Commission, they have a future of gas workshop where they're determining what to do with the future of gas. I know the politics in Illinois and Missouri are very different, but we're educating and working with the ICT to educate on, well, if you want to do these things, here will be the consequences. We have the industrial sector that relies heavily on natural gas. And it does so because of thermal energy the industrial sector needs, and we'll be talking about some examples. So if we want to move from the future of natural gas, we have to be aware of how that's going to impact the industrial sector. We're also working with the Minnesota Public Utility Commission in their thermal energy networks working, educating them on if they move to thermal energy networks, what will be the consequences for the industrial sector, for large energy manufacturers. Not positive or negative, just what might happen. And so we do a lot of this work with stakeholders to educate on just how policies might impact large energy users, especially for those that have energy companies. Which gets me to discussing some of the onset energy technologies that we recommend, that we most often recommend. This is not a comprehensive list. So these next three slides, I'll go through pretty quick. I think most of us are familiar with some level of these technologies, but I chose these because in all the technical assistance we provide in the Midwest, and this is, Kansas and Nebraska, all the way over to Michigan and Ohio. These are the most common technologies that we recommend. We find are positive impact and can get solar. So solar PV, it's generally going to only take a small bite out of the electric load of manufacturing of large industrials, but it usually comes with a very quick payback, very positive ROI. And so a lot of the providing some high-level costs. This is from, I think, 2003, 2004. The picture on the screen is from a facility in New Jersey, a Sunoco facility that has a 1 megawatt rooftop mounted solar PV. For a lot of sites we work with, that's going to be a small bite of an energy apple, but one that looks good as a local material, and two that comes with a very quick payment. So we've been analyzing a lot of this in the Midwest region and recommending a lot. The other technology is no surprise, is wind. This has gone from being primary utility driven, I mean, it's still primary utility driven, but we're seeing more and more sites wanting to explore adding wind turbine. One, because the amount of space needed to generate a lot of electricity with solar is just not readily available for the industrial sector. Understand that a lot of acres to generate power for solar PV. So we're seeing sites when they can, and they have the space to work, they have the clearance from, let's say, local airports or other zoning and these regulations, looking at on-site wind. Picture on the screen is from Whirlpool, one of Whirlpool's plants in Ohio. It's a number of 1.5 megawatt wind turbines. There's 4 on the screen. I think there's a couple more installed at this facility. So they can be an incredibly cost-effective way to receive for industrial projects an average installed cost of $3,000 per kW installed. But at the heart of all of the analysis we do is combined heat power. And we've been running our center since 2004 when we just did combined heat power. So I've been giving this talk, especially to my family, a lot when every Christmas I would explain what combined heat power is if nobody's heard of it. I know a lot of folks in this room have heard of it, but I'll give a brief overview. Combined heat power is an umbrella term for a suite of technologies that at its core generates useful electricity and thermal energy from one fuel source. So unlike wind turbines or solar PV, this isn't a single technology. This can be a bunch of different technologies. So there's the electric generation technology and thermal recovery technology, both of which can be, there's multiple options. So the top schematic that you see is what we call a topping cycle. That's one of the most common. And that's where you have the electric generation technology first. So most common of that are combustion turbines, which the University of Missouri, that's what we get into your example in a sec. And then reciprocating engines. Just like other engines or combustion turbines, fuel is combusted, it turns a generator, and the exhaust then is captured to be used productively on site. So unlike our cars that have a radiator that get rid of the hot air so it doesn't ruin our engines or the exhaust in tailpipe, CHP reciprocating engine will capture that exhaust, capture that radiated energy to generate hot water or steam. The same with the combustion turbine. Unlike a jet engine, it uses that hot exhaust to propel a plane. We can now capture that hot exhaust to generate steam on site. The big benefit of this is now we're pushing fuel use efficiencies of 70, even 80%, which come directly with a cost reduction, an operation cost reduction for the site, but does require an initial kind of investment. Because natural gas infrastructure is usually safer from natural disasters, this provides on-site resilience. Because we're using gas more efficiently, some of the lower emissions as well. And since gas is one of the cheaper fuels, especially in the United States, this comes with a lot of cost savings for the industrial sector. So, and the bottom schematic is what we call bottom cycle. This is the original electric generation technology of a boiler that generates steam. Steam that goes through a steam turbine to generate electricity, and either condense it as water or is spit out in the different pressure steam to be used on the facility. So here are just a number of technologies that we see in combined power configuration. Again, this is an umbrella term that involves, it refers to many different technologies. So all these technologies have different characteristics and are used in different applications. And our center helps industrial sites and other large energy users determine if combined heat and power is right, and if it is, what technology are we talking about? And that's largely dependent on the thermal modes. You can have chilled water, hot water, you need direct hot air, the paper industry does for drying, you need steam, whatever that is going to help us determine what technology to look at. Here are some costs and average efficiencies from the year 2003. So these might have increased, probably have increased since then. So with that out of the way, those are, at the heart of all of the technical systems, those are the technologies that would be the heart of what we do. We of course explore lots of other technologies, and I'll be going through a handful coming up. But sites are more and more interested in looking at ways to generate thermal energy that isn't necessarily combusting coal or combusting natural gas. So we're looking at a lot of industrial heat pumps. Although I have yet to see one industrial heat pump pencil out in the Midwest that has such cheap natural gas prices. We also do a lot of battery storage. And I didn't include that on here because it's strictly speaking not an energy generation technology, but we do work with a lot of battery storage as some case studies about to run through. And then other sites will have certain technologies that I've heard about, certain technologies that perhaps they've gotten a quote from, or looking for a vendor from, that they want us to help vet that. And that's part of what we do. Is we don't just start the technical systems, but we'll work hand in hand with sites to vet any engineering documents or vet any proposals that come their way to make sure everything is above board and looks good. So one of these emerging technologies that we're seeing more and more and doing the analysis for are this thermal storage. And this is different from the more commonly used thermal storage of you just put a big tank of hot water, a big tank of chilled water, which are still great tools and incredibly inexpensive. But now we're seeing emerging thermal storage for like hot drinks. So you can store thermal energy that can generate steam when you need it. Some type of thermal battery that you can either use on exhaust to charge the battery or electric resistance. And so that's coming online more and more. There's an installation not too far from my house in New York. It has a thermal battery. We have, again, it's pencil out in the Midwest. So with that, I have a number of case studies of sites that install on-site energy. This ranges from the industrial sector to commercial. Some sites that our center has helped provide technical assistance to, some sites that we have. So I want to start with So Prayers Engineered Wood has a combined heat and power biochar facility. So this is a manufacturer of laminated veneer wood. And in 2007, their gas bills were forecast to increase by about $1 million, from 1.5 million to roughly 2.5 million. And they use natural gas in their boilers to generate steam, and steam was used to dry the veneer, to dry the wood. And then steam was also used to to help with the log, conditioning logs for the manufacturing purpose. So because natural gas was increasing so much, they wanted to find a different solution. So in 2007, they built a biomass boiler. They installed a biomass boiler to use the wood residue that they themselves created on site to generate up to 100,000 pounds per hour of steam at 850 psi. That steam was then sent to a GE 10 megawatt extraction or double extraction turbine to generate electricity. The steam was extracted or is extracted at two pressures, 300 pounds to dry veneer and 65 pounds for log conditioning and to make hot water through steam and hot water heat exchangers. One of the coolest parts about this project is that they only use 30% of the electricity they generate. They send the rest back to the community in Ryan's. And so during the weekends, when this facility isn't in full operation or not in operation at all, they send all of their electricity back to the Ryan's. They have a purchase agreement, they're a qualified facility under FERPA. And so they have a pretty good rate that they can sell this electricity back to, making their town more resilient because they have a local source of electricity and giving them a revenue stream. So I thought that was one of the coolest aspects of this, is that they're providing so much more for their community. So this project had a 7-year payback with cost savings of roughly $500,000 a year. Now, since then, and the big reason for this project going into the ground is gas prices were forecast to increase for them by $1 million within like 2 years. So something incredibly significant. Since then, gas prices have decreased, but they're still seeing so much savings from this project that they continue to. But yeah, it's an incredibly cool project, and I have a quote from Rob Schreier, the executive vice president, about how their CHP system gives us more control over our destiny. He's also talked about how it gives them additional revenue streams. They use CHP system to produce biochar, which is a CO2 dense material that they can sell and in a way I'm not really familiar with, but they get carbon credits for it, but certainly in Europe, so that's another revenue stream. And then they can avoid, because they're producing their own fuel with woody biomass, they can avoid having to purchase natural gas entirely. So the other, so this is a non-industrial case study. This is a residential and commercial case study. And it's a bit specific because it used Facebook money. Meta gave a lot of money to this project to make it happen. But this is a community in Menlo Park, California, that actually just went in the ground a little over a year ago. And it is a community that's housing, I think, 13 or 14,000 people. It's right here. Yeah, 45 residents in a 3,700 square foot campus. And the goal of this community, the goal of this development was that it could be energy independent, that it could have enough capacity to act as a safe haven in case the grid would go down. And so they installed a 546 kilowatt PV system with a 367 kilowatt or essentially 1,400 kilowatt hour battery storage system. And then to reduce the electric impact on the grid, they installed solar thermal. There's 360 kilowatts of backplate heat collection. And so, of course, California is in one of the more wealthy neighborhoods, so they have a pool, and they avoid a lot of energy costs and reduction in utility charges. And so this community has not only apartments and condos, but they also have a senior center, a community center, a youth center, a rec center, and a local branch of the library. And if the grid were to go offline, which I think in the news probably happens not infrequently, this could run on full load for 24 hours, and if the outage is going to be longer, emergency load could last a month, much longer. So even though they did receive money from that from Facebook, they still chose a system that had a net positive payback. So this system is going to pay back for itself, it's estimated in 15 years, and it just went online last year. So yeah, and even with grid outage batteries, we were able to power the entire community for 24 hours or for longer if not essential system. So one of the other non-industrial examples I have is a hotel or retreat in Hawaii. Now, Hawaii is famously difficult for providing new electric capacity. If you build a hotel remotely, if you build a house remotely, it's going to be expensive and difficult to get a distribution line. Now, the utilities, like they do in Missouri, they do in Illinois, have an obligation to serve. So if you ask the utility for electric service, they by law have to provide it. You have to provide the costs. So this retreat asks the utility, well, we need electricity, please serve us. And they got a bill for $100,000 saying, okay, to connect you to the grid, it's going to be $100,000. They said, we think we can find a better way to spend that money. We're gonna do it. And so what they did is they installed a small wind turbine, 6 kilowatt wind turbine. They installed 26 kilowatts of rooftop heating, a battery storage system of 155 kilowatt hours, and then some backup diesel just in case. All of that costs only slightly more than the $100,000 they would be charged for distribution. In addition to that, they're not spending money on the utility electricity, they're producing it themselves, for much lower cost on site. So this was installed in 2015, and since then they've seen $120,000 in cost savings. They've learned a lot of different lessons. One, they replaced another wind turbine. This doesn't really apply to us in the Midwest, but I saw it was too close to the ocean, so there was too much corrosion from salt that they had to, when they do get it maintained, they're going to have to recite that in a place that doesn't have so much salt corrosion coming from the ocean. But yeah, so this, the facility operates 100% on these assets, on PV, on the wind turbine when it is operational, and the battery storage system for overnight. And then the backup diesel. The site has never once, in I think about 10 years it's been operational, had an electric outage. They've never had a power outage. I'm not going to talk about this too much because I know Jim's in the back and I don't want to get anything wrong because, and we also kind of gave this presentation a year ago in San Francisco, but University of Missouri has an amazing microgrid system. Just, if you don't know about it, and I'm assuming we're all here in Columbia, a lot of us probably do know about it, it's just fantastic. In putting this slide together, I learned a couple of cool things that I'm getting perhaps a little bit jealous about. Missouri, I didn't know, was the first land grant west of the Mississippi, and it was one of the first, and the first west of Mississippi to have electric generation, because Thomas Edison, 1886, something like that, donated equipment to the University of Missouri. So as a Nebraskan, I'm definitely jealous about that. But this is, I don't even know where to start. All of this HV technologies, University of Missouri kind of has most of them in that back. There's steam turbines, they have extraction steam turbines, they have gas combustion turbines that recombust the exhaust, leaving them to produce a ton of steam. So this system produces steam, hot water, chilled water, electricity off the campus. It does so in combination of natural gas, woody biomass like renewable wood, a little bit of coal, although that's been increasing every single year, and even some of that way to solar level. So I won't get into this too much because when you have a facility here, you don't want to make a mistake in describing the system. But I will talk directly about two sites that we have provided technical assistance. So our center, when we were just in the Midwest, combined heat power technical assistance center, worked with the Indianapolis Gatorade facility, worked with PepsiCo to size on-site energy for their site. So in, I think, 2016, 2017, PepsiCo had these had some pretty significant sustainability goals that they had to meet from PepsiCo corporate. And Andy Lampera, who's the sustainability director of PepsiCo, looked into a bunch of different technologies that they could use with Indianapolis Gatorade facility to meet their sustainability goals. And by the way, this facility produces every flavor of Gatorade in every size. So if you've ever drank a Gatorade, there's a high likelihood that it came from this plant in Indianapolis. And so what they found in their study about how to reduce greenhouse gases cost effectively is that cogen was one of the most effective technologies when compared to LEDs, condensing economizers for their boilers, solar PV, and line improvements. So out of all of those technologies, cogen had the lowest price per avoided metric ton of CO2, natural gas-fired cogen. So what do they go with? This facility uses a lot of steam to manufacture Gatorade and a lot of hot water. And so they went with 3 CAT units, 3 1.2 megawatt CAT natural gas engines. These, based on their electric and thermal loads, all of these are set to electric load all. They have such a high thermal load, regardless of how much they're generating, they're always going to be able to use the thermal energy. So these engines produce 2 types of thermal energy. They produce steam from the exhaust coming out the back. The exhausts from these engines are roughly 500 to 600 degrees Fahrenheit, and they make steam at 115 psi. And then they take all the jacket water, the radiator system in our cars, and collect that so they can produce 225 gallons per minute of roughly 190 degree Fahrenheit hot water. And so they'll take and use all the thermal energy these engines can provide. So these engines rank up and down solely based on the site's electric load and not thermal load. They're never wasting any thermal energy. If these engines are operating, they're using every BTU of thermal energy coming off the back. So the total system cost of this, install cost, engineering, interconnection, et cetera, was $60 million. And it paid back for itself in 6 years, which for a facility like PepsiCo is, and some of the other industrials, if they're in the room, 6 years is a long time. When we work with industrials, 18 months, 24 months if we're lucky, but it's usually we need to have a system, a big capital project that can pay back in 18 months. So for them to be willing to take a 6 million or a 6-year payback was pretty extraordinary on their perspective. But it did pay back in 6 years, or technically it's set to pay back in 6 years because it went into operation at the beginning of 2019. And so it should technically be paid off now. But I think it would pay off even in a year or two. And then the emission saved on the bottom. So over 10,000 metric tons of CO2 equivalent, even though it uses natural gas. So I just want to read this quote from Andy. Utilizing CHP within several of our manufacturing facilities is a key element of PepsiCo's commitment to sustainability. It improves their energy efficiency, reduces the carbon footprint, and reduces their overall utility costs. The Indianapolis Gatorade manufacturing facility is our latest CHP project venture. Since installing this, PepsiCo has looked at CHP at a number of other facilities nationwide. But we did the initial technical assistance on them and help them come to the conclusion that 3 endpoints was the best. So my last example is I think one of the coolest projects that we've worked on, and one of the coolest projects that outside of the University of Missouri that our centers have worked on and it just exists in the United States. So the Ford Motor Company has a REC, a research facility in Dearborn, Michigan. And this facility needed a lot of system upgrades. And in 2018 and 2016, they started the master plan of updating the facility. And how were they going to? The facility is 6.5 million square feet, which includes office buildings, lab facilities, dynamometer building, several wind tunnels, and the project construction of a new, they needed a new central energy plant to run all the upgraded equipment. And so they looked at a number of different ways to do this. Ford really didn't want and still doesn't want to own and operate physical plant equipment. They don't want to make energy, they want to make pumps. And so they contracted with energy service company, DTE Vantage, at the time it was called DTE Energy Services, that you see on the slide, to come up with a bunch of different options And the option they showed is a really cool option. DOE, design, build, own, operate, maintain. So this third party designs the system, builds the system, owns the system, maintains the system, sells all the energy, not back to Ford. They sell the electricity directly to the electric utility. Because this is in front of the meter instead of behind the meter. So all the electricity goes to the regulated utility, and all the thermal energy goes to Ford. But the configuration is such that if the utility, the greater utility in Dearborn, were to have a blackout, circuits can be shut. So this system could island the Ford plant. So it's like having your own power plant that the utility owns, but if the utility grid were to go on a blackout, that plant would still be operational and still serve your load. So what's in this system? Maybe I should have started. Well, it's powered by two 14.5 megawatt solar turbine Titan natural gas combustion turbines. So on the back of them, they have heat recovery steam generators from Redmond. They're each capable of producing 185,000 pounds of steam, which drive a steam turbine and provide hot water for space heating and for facility use. They also have a geothermal. They use heat pump chillers. The steam goes to heat pump chillers to produce chilled water. They also have mechanical chillers to provide chilled water. They use the geothermal to augment the chilled water, depending on prices of natural gas. They have heat exchangers to produce hot water from the steam. And so you see this kind of complicated box. One of the other aspects that I realized I did just get wrong is that the combustion turbines are actually owned by the utility and operated by the third party. So the utility does own these assets, and they contract everything out to this third party. So the kind of vertical box you see in the middle is everything that's managed by the third party, and which is ET Energy Services. You have the thermal energy up top contained, and the or the electric energy up top contained, and the thermal energy at the low equilibrium. Ford campus is on green. Ford doesn't own any of this equipment. They just enter into purchase agreements for the thermal energy, and then just buy their electricity regular from the utility. So their rate doesn't change, but they do have access to uninterruptible electricity in case the grid would go off. And because it's this design, build, and operate, maintain, Ford didn't have to put any capital up to install this. They entered into a long-term performance contract, long-term contract with DOE Energy Services. That makes sure that when all of the risk is on DOE Energy Services, and Ford just pays for their energy. So now Ford has this resilient and reliable source of steam, hot water, chilled water, and electricity, and didn't have to put any capital down to make this happen. It's an incredibly cool project. We're seeing this we're seeing this model happen more and more throughout the country for a couple of different reasons. One, there's no capital, or very little capital outlay that the industrial sector manufacturers have to do. And two, because it can be more resilient. You can build all these, you're not fighting the utility company. So in a lot of parts in the Midwest, and no offense to the utilities here, but the electric utility can present some barriers, make it difficult to some extent. And that makes sense to a large extent. They have a business model, they want to make sure that their grid is secure and safe. But when you bring the utility into it, when you allow them to own the asset or control the asset, then it makes it much easier and everybody's a winner. So very good question. So those are the case studies I have. Right now, I want to go into what our technical assistance looks like, what type of analysis we do, what that looks like, and have a case study for a site that we have built, and the decisions they made. So the intention of our program from the Department of Energy is to be this neutral third party. Essentially, to be the first step for businesses to decide if they want to do on-site energy. We will analyze all different technologies, and based on your inputs, based on your grading criteria, we will come up with the best technology or this suite of technologies that meet your goals. Now, at the very beginning of my presentation, I mentioned that cost savings is still the #1 factor in making these decisions. But some businesses have, okay, we need this to pencil out, we need to have a positive ROI, but we also need to see a 10% reduction in scope 1 and 2 emissions, or whatever that is. Or we need to be able to run uninterrupted during the blackout for 24, 36 hours. Help find us the best combination of technologies to meet that. And that's what we do, that's what our engineering team does. So we get data from the site. Sometimes, but rarely, we'll do site tours, walkthroughs to see where all the equipment is located, how it works. But we'll make a pretty big data report from the site. Our engineering team will meet at least virtually with the site, and then model that to come up with what technologies we can do. And so here's just a really high level. When the analysis looks good, we'll go out to the private sector and make quotes for equipment. So I mentioned we'll get quotes for steam turbines or combustion turbines or solar PV or wind, whatever that is, to take cost factors that are published from the Department of Energy and solidify those numbers. Then for the site, if the site likes what they see, if the payback's within their tolerance, if the emissions reduction they want to see is within their tolerance, if whatever rating criteria is met, we can then help that site proceed. And that looks like a bunch of different things. One that can be helping a site write a request for proposal for engineering companies for design engineering. Or it can be to contact or work with OEMs to get quotes for equipment. It could be to outreach to the electric utility to start discussing interconnection procedures. It can be reviewing permitting guidelines to see what type of permitting is going to be necessary. The point of our center is, one, farms, never get in the way, but also be there to provide neutral, unbiased information that can help the site proceed with installing the equipment. We don't do the design engineering work ourselves, but we have engineers that have worked on-site physical plants for a number of years. They can review drawings, can review system specifications. So this is what for our high-level screening at the very beginning of this process looks like. It just takes into consideration business as usual, and then goes through a number of different technologies with the high-level results of each of these technologies. Simple payback, peak demand reduction, thermal output, emission reduction, all of these things. So you can clearly see what system or combination of systems best meet their goals to help make an educated decision. Or not educated, to help make an educated decision on how they go. I did provide one case study of a partner we worked with, and this is an alloy manufacturer, Haynes International, that out of Kokomo, Indiana. They produce a high-grade metal alloy. They have high thermal needs and high electricity needs, and they worked with the Better Plants program out of the Department of Energy, which are essentially a member, and they worked with the TAP program to analyze a number of different technologies to determine what was best for them. So the site goal is to determine if Onsite Energy can meet their needs, and they wanted to see specific results from REOP. REOP is a modeling tool published in the National Renewable Energy Lab. It's one of the many tools that we use to help decide what technologies to look at. And so they had two different scenarios they wanted projects created. The cost savings, what combination of technologies is going to best reduce our costs? And then two, what combination or technology is going to reduce our emission, 20% scope 2 emission reduction. They had three scenarios: a 4 megawatt PV system, a 4 megawatt PV system plus the battery, the battery and storage system, and a 1 megawatt microturbine system. The Capstone small microturbine that generates exhaust at roughly 500 degrees Fahrenheit and convert that hot water to heat. And so on the screen here, you see the results from just the first two technologies, the battery and solar. And so when you cost savings only, and you model whatever size you want, we found that a roughly 4 megawatt battery had a 4-year payback. No solar. The electric rates, this is Indianapolis Power and Light, that had such high demand rates that a battery would do a really good job of reducing those demand charges in the peak, and a 4 megawatt system we modeled would pay that for itself in 4 years. But then we also modeled the payback period for if they just went with solar. And you can see that's much higher. That's 7 years. So I'm looking at the middle top box. It reduces emissions by 5%. It should come as no surprise. Battery by itself doesn't reduce emissions. It's just shifting when electric load, shifting your electric load. The solar does come with emission reduction of 5% and has a payback for 7 years. And then let's put both together and see what the results are. So that would be a 5-year payback and also a 5% emission reduction. Now we look for the sizing for these three on the bottom. So as I mentioned, a battery we found would be about a 4 megawatt battery that has the smallest payback. That's the bottom box on the left. Now 4 megawatt solar, no surprise, 4 megawatts. Now when we put them all together, what sizes are we looking at to meet best in the Well, that's still the 4 megawatt solar system and the 4 megawatt battery working together. So Graeme, who's the director of environmental health and safety for International, talked about using this as a tool and helping identify technologies to meet all of their factories using that North Carolina and Louisiana sites in addition to this one in Oklahoma. This analysis was only done last year, so I don't know which of these, if any, they're proceeding with. The impetus for doing this is they got a quote from a microturbine distributor, capture microturbines, so they had this quote. They had this, why don't we look at other technologies as well? So I don't have the results from the microturbine, I have the results here from the solar and battery. But this is emblematic of the type of analysis we do when we provide the industrial sector. Now, this is pretty on the high end. This would be one of our first steps before we dig in much deeper. And then briefly, to end my presentation, before answering any questions, some other activities that we do. I mentioned technical assistance in the bread and butter of the TAP program, but we also do a number of other activities. We work with industrial facilities to educate on the benefits of on-site energy. We work with community organizations to also, discuss the benefits. One of the big topics that we discuss is to community organizations is that, in fact, natural gas powered equipment, such as combined heat power, can reduce emissions. It can, significantly reduce emissions depending on where in the Midwest we are. And that's something that a lot of people don't see, it doesn't make most sense, and I understand that. We're burning natural gas but at the same time saving emissions. So we'll work with state energy offices to inform their constituents and to inform them of potential barriers that exist in their territories. What programs exist elsewhere, what programs should they implement? All of this neutral, unbiased information. I mentioned 2 examples of working with public utility commissions to educate on outcomes and barriers and opportunities. And we do the same with trade associations and utilities and energy service providers as well. So intended outcomes, when we have these, when we do meet stakeholders, is we just want to accelerate pathways for on-site energy, for developing on-site energy, for installing on-site energy. We want to build better partnerships across the industrial sector. We want to help drive conversation and make connections so the industrial sector knows who to talk to, where to get information from, where to double check things. And yeah, at the end of the day, it's all about providing technical assistance to help businesses in the Midwest, businesses in this country make informed decisions, the best meet their goals, the best become more resilient and save money. So the Department of Energy has a number of other resources. We have a number of fact sheets on various on-site energy technologies. I think cover 3 of them in detail, but there are fact sheets on batteries, on thermal storage, on heat pumps, etc. We have a number of testimonials. I believe the video there is a testimonial from from Whirlpool about our centers and our program. So if you're interested in being there's a lot of good resources. If you have to answer any questions around the data too, you want to stop and talk about it slowly or talk about it. So thank you very much. Questions? How do you want to be done? I'll bring this one. All the other. Thank you for that. So thank you for the presentation, and while I watched it, I couldn't help but think about all the cost analysis in the presentation. When I go into a fast food place and see calories, is it possible that in a world where we now have tornadoes, which we didn't have in my 50 years of just a few miles this way, and we still haven't internalized the cost of, like, I have to pay to have my trash picked up, but I can run a diesel generator for free, and it was commendable CO2 reduction, but would it be, have you seen, or would it be possible to side by side show paybacks and costs in terms of insurance or other risks? Is there a formula for that exists with our Department of Energy in these presentations? The short answer is no. That is a much more, that's a pretty interesting question and deserves a much longer answer. And that we can certainly do that analysis, but it's something that our center hasn't really done much. So you're talking, if, you know, what would your insurance rates be? Tell me if you get this wrong. What would your insurance rate be if you installed one technology over the other, or didn't install anything? Or monetizing the value of reliability or resiliency in case the tornadoes, you know, or in case some catastrophic event might happen. Yeah, we've been asked a lot. That's a good question. We have been told not to. There are no factors we can use. If provided a monetization factor like that from a site, we will happily incorporate it into our analysis. But that number is going to be different for all businesses. So if we just focus specifically on like production average, so we work with a tire manufacturer and they suffer an outage, they not only lose, you know, they lose the production line, but then they have to clean everything up and they could be out for a day or two. And they can put a cost to that and say the value of resiliency is, you know, we'll save $1 million a day if we can operate uninterrupted. And so we can take that number and put it into our financial analysis to say, okay, business case, there's not this benefit, but if you were to install PV with battery, it was large enough. By itself, it might not pay for it, but now with this resiliency factor, it does. But because it is so different between industries and between businesses, we always ask about that OEM profit. That good question. The other question? Go ahead. If the Onsite energy program has done any work with data center developers or has plans to work in those 5 years. I know that they have a pretty high capacity load factor and there's not a lot of room necessarily for energy efficiency. The concept of the trade stuff on the other side. I couldn't hear what type of developer did you say? Data science. Yes, the question again. We get this a lot. We have worked with data centers. One of the difficulties is that they don't, the only thermal energy they need is chilling. And so we have looked at sites where we can, one of the technologies that I mentioned, defining power as a suite of technologies, is an absorption chiller. And that's taking thermal, like hot air or water and produce chilled water. I'm not an engineer by training. I think some of you are. When I first learned this technology, it blew my mind. But it's essentially what I refer to, I refer to servers. But anyway, to answer your question, yes, we have worked with data centers to size on-site electric need and then to use the thermal energy to provide some type of chilling and absorption chiller. The problem is, that's a more expensive solution than just buying gas generators and generating electricity and buying cheap chillers to generate chillers. And so, or if they're lucky enough that the utility has capacity, it's getting an interconnection from the utility. So in certain circumstances, I mean, in all circumstances, it works great technically, but it only pencils out in certain circumstances where, for some reason, they, the cost of electric chillers is going to be take so much time to deliver or going to be so expensive. So there's not much we do with data centers, unfortunately.
Maybe to follow up the question a little bit, but thinking about data centers and wondering what you do with them thermal, but also thinking about manufacturing and electrified process steam. Are you looking at SMR zone?
I wish. Our purview is technologies that you can purchase. So if and trust me, we get asked this all the time. And when I go to big conferences, the SMR talks are kind of my favorite. Unless I can get a quote from a provider, we can't really look at the technology. And our engineering team would love to look at SMR. Our sister school at Champaign-Urbana has a reactor, like a student reactor, test reactor, and they, I think, use it to some extent in the CHP configuration, but it's mostly the training and the meter as well. But so the answer is no, unfortunately. Hopefully that changes.
Quick follow-up.
Yeah.
What? The data center and developer came together with a turnkey proposal package, price down and everything, and couldn't get it.
Absolutely. Yeah. And we do, outside of SMRs, we do that a lot. Like folks that come to us and say, we got a bid, or we got, your spec sheet, can you check it to make sure everything makes sense and looks good? And we'll do that. If it was SMRs, our engineers would really love to do that. So yeah. Very much.
Yeah, well, I do have a question for you. Have you guys worked with the regional opportunities or the regional lack of engagement? You're in the central region. We've always heard that efficiency for industrial is hard because our energy is so cheap compared to the coast. But your examples were spread throughout the country. In your work, if you looked at that, talk to the collaboration across the country to figure out who is or why are folks in the Midwest not taking advantage?
I can answer the question specifically with gas-fired cogen. I don't, because that's what I'm working more on. But yeah, so we have looked at all the states in our Midwest region, the 10 states in the Midwest region, to see why gas-fired cogen works in some and doesn't work in the others. And it's a frustrating answer. Well, two answers. One, it's complicated, which is frustrating in us figure anywhere. And two, it largely depends on the electric utilities costs and prices. So we are fortunate enough, and I know it doesn't always feel like it in there, but we're fortunate enough to have some of the cheapest electricity in the country. I live in New York, and trust me, that my electricity bill skyrocketed when we moved out of the Midwest. And so even though gas is cheap here, when you're looking at gas-fired cogen, you're looking at the spark spread, the difference in cost between natural gas and electricity. And there's a little formula I don't need to get into, but essentially the cost of electricity just isn't expensive enough for it to pencil out all the time. I'm not advocating in any way that we have more expensive electricity, definitely not doing that, but that's one of the barriers, shall we say, to that technology. Now, the other technologies like wind and solar, those are new for our shop the past year and a half. So I couldn't speak on those. I know a lot of state policies, local siting, local zoning, that type of thing. But when it comes to guys like gas, we're going to largely price electricity determining how it's going to be.
In your mission statement, most places have mission statements, I assume. Does that include anything to do with the environment? What are your goals to reduce the production of greenhouse gases, which is the primary source of pollution in the atmosphere?
A great question. I'm up here speaking as the Department of Energy, not as myself that works at the University of Illinois. I will say that our mission statement concerning the topic you just mentioned has changed in the past 2 months to focus on industrial resiliency and competitiveness. That's all I'll say on that. Yeah.
So the solar array.
One more. All right.
One of your earlier slides, you showed the solar array that within your department, like across the DOE and even beyond, I've seen like a lot of it, and there's one thing that the government is very good, provides these maps of transmission efficiencies and so forth, and transmission lines, and you mentioned some of the cost analysis and benefits to the industry or the owner that's making a decision, and in cooperation with the utility, a win-win. Can you come across these sort of things where we can alleviate or improve, the capacity to transmit, improve the resiliency of the grid? That's one of the advantages of distributed.
Oh, absolutely.
Like solar.
So we haven't mapped our program. Other parts of DOE might have done this that I'm not aware of. We haven't mapped transmission constraint or distribution constraint and where the benefits of DG would be specifically. And I think today or tomorrow, folks from MRO and Midwest Power Pool, they're up right up. So that would be the question. I do know. I don't know if folks in this room have read it, but NERC put out a report, the 2024 reliability report. Show up names who's seen this or knows about it. Yeah. So you know probably where I'm going with this is that in MISO especially, there is forecast to be a lot of capacity shortfalls. And so the businesses we're working with have seen this and are kind of terrified that we'll be operating in a summer day and all of a sudden the grid's going to go offline. Not because of tornadoes, but because of it's just a hot day. And so that's driving people to talk to us, but I don't have a map that says, or like I don't have a resource to say, like if you put it here, that'll create the most benefit to the grid. But they
There you go. You guys know you have to bring up. Any other questions? One more? All right.